Hello everyone, good day and welcome to this lecture. In this lecture we will continue with reaction modeling using Aspen Hysys. So we'll continue from where we stopped in the first and second lectures. So here I would show you how to specify some of the reaction models that we have, right? So we are in reactions. So from the component list, I've already added the components I'll be using for this illustration. Then I've also added the fluid package already. So now we are going to be specifying some of the reactions, right, from the reaction set, right? So we are working with the reaction set. In the previous video we modeled the chemistry sets, so we are working with the reaction set in this case. So from the reaction set, the first thing you need to do is to click on reaction set and then click on add reactions. So from reaction set, like we said earlier in the previous video, you have five models: conversion, equilibrium, heterogeneous, catalytic, kinetic, and simple rate. Now in this particular tutorial we will deal with just the conversion and the equilibrium. Then the heterogeneous, catalytic, kinetic, and simple rate will be treated in a subsequent video or subsequent videos per se, right? So we are dealing with just the conversion and the equilibrium in this particular tutorial. Now when you are selecting your model, you can determine which particular data bank was used to select your components, right? So for example, if you used the Hysys data banks, so you have to highlight or click on the Hysys data banks. But if you use the Aspen properties database to choose your components, you have to click on it, right? So in this case I use the Hysys data banks. If you can see my cursor, I use the Hysys data banks. So now if I want to add a reaction, for example, and I leave it at Aspen properties, and for example I use conversion, right? I use conversion, then I click on the reaction window, you will find out that there is no reactant in the there is no component in the components section of the reaction window, right? Because I chose the wrong data bank. So you must ensure to choose the data bank you selected your components from. So I will be deleting this. Okay, if you want to delete, you can just click on delete reaction. So I'll just delete that, and then I go over it again and I change it back to Hysys data banks because that was where I chose my components from, right? Then I can click on the particular model I want to use. So in this case I think we'll start with the conversion. So for conversion, just click on add reaction. When you are okay with your reactant source, just click on add reaction, and then you get the opportunity to specify a conversion reaction, right? So basically the conversion model works with the specification of the conversion of that particular reaction, right? So if you have a reaction and you have its conversion, you can use the conversion model, right? The conversion model. So we have some reactions we'll be specifying in this particular tutorial, right? So these are the reactions we'll be working with. So we have 3 reactions, right? And we'll be modeling all of them in this tutorial, right? So we have reaction 1. We can just add 2 more reactions, right? And then add another reaction, all from the reactant source Hysys, right? So we have all of them and we can specify them based on what we have here. So first we have for reaction 1 we have let's see, we have CO plus H2O. We have CO plus H2O to give you CO2 plus H2, right? CO2 plus H2. So we are working with this. Now we can specify the stoichiometric coefficients of each of the components involved in this reaction. For reactants is negative, and then for products is positive. So we can balance up the equation. So we have this. Yes, so you see your balance error. Your balance error is 0. That guides you as to know when your equation is balanced, right? You should have a balance error of 0, right? Then for the bases, you specify the base component and then the conversion, right? So most of the time the conversion is specified under this CO section, right? So for example, if you have 60% conversion, you can just basically specify it here. But if you have a complete equation for your conversion, you can specify your C1 and C2 as well, right? But most of the time, conversion is just specified using CO, right? So you just specify the percentage and you are good to go with that particular reaction. So in this case, the conversion is 90% conversion of water. So our base component is water instead of CO. So you can actually change that here in the base component section. Then you can now specify your conversion, right? So it's 90% conversion of water, right? So before you specify that, you will still be having the not ready you'll be having the not ready message here in your reaction window. But when you are done specifying a particular reaction, you have the ready message, right? So you know you are done with specifying that particular reaction, and then you can close the reaction window. So basically you also have the tick box here. So basically we'll be doing the same procedure for the other reactions, right? So we have CH4 plus H2O, CH4 plus H2O to give us let's see, CH4 plus H2O to give us CO plus H2 plus H2. Yes, so we can also specify the coefficient. So we have -1 here, -1, -1, then 1 and 3, I believe. Okay, so you see the balance error. Then we have our base component as water. Base component is water with 90% conversion. So we can change this to H2O, and then we can specify the conversion, and this is also ready. Then we can finish off with the last equation, reaction equation, which is ammonia production. So you have nitrogen plus hydrogen to give you ammonia. Nitrogen, let me see, N2. Okay, N2 is not in this. Yeah, N2 is 1, 2, 3, 4, 5, 6, 7. N2 is not in this. Let me add N2 to the component list. So I have added N2 to the list now. Let me see, N2 plus H2. Okay, so we have N2, which is nitrogen. Let me see. Okay, I have to delete this reaction and specify it again. So add reaction, conversion. So for this we have nitrogen plus hydrogen to give ammonia. Yes, so 0.5, then 1.5. so we have 0.5, then 1.5, to give ammonia, so it's balanced. Then we have conversion of nitrogen as 80%, so base component is nitrogen, then conversion is 80%. So we are done with this, right? So now the next thing is to attach these reactions to the fluid package that has been selected. So all you need to do is click on add to FP. You have add to FP here. Click on add to FP, then add set to fluid package. So you just click on that. So once you click on that, you are good. Now before we go to the simulation environment, now when you are specifying one reaction, right? One reaction in your reaction set. Once you specify the reaction and you add to fluid package, you are good to go. But when you are specifying multiple reactions in a conversion model, you would have to specify the order in which these reactions take place, right? You have to specify the order, and that is where this ranking right here comes in, right? So you use this ranking to give the software the idea or information of which reaction comes first and second, and like that, depending on the number of reactions you have, right? So for example, analyzing this reaction set that we have the first reaction, second, and the third. Now you will notice that let me see. Okay, for example, the product of the first two reactions is required in the third reaction, right? So it means the first two reactions have to occur first for you to actually have the third reaction possible, right? So because in the first two reactions, hydrogen is produced, right? So these first two reactions have to occur before this third reaction, right? So that's how it works. So sometimes you may have the first reaction, the product may be the reactant of the second, so the first has to occur before the second, and then probably the product of the second may be the reactant of the third, and then the second has to occur before the third. So you have to look at those things when you are specifying multiple reactions for conversion models, right? So that you can order your reactions properly for accurate results. So that is what we are going to be doing here. So now we can rank the reactions before we go to the simulation environment. So here we have a rank of 0 for each of them. What this means is that all reactions are occurring at the same time, which is impossible, right? Some have to occur before the others. So yes, so what we do is we start our ranking from 0. So the first reaction has a rank number of 0. Then you can now start specifying the others. So if the first is 0, the second is automatically 1, and the third is 2, right? So you have 1 and then you have 2. Then you click enter, right? So once you order them consecutively, right, you can close the ranking window, right? You can exit the ranking window. So we are done. We have specified the reactions, we have added to fluid package, and we have ranked the set, the reaction set, right? So we can now move over to the simulation environment, right? So in the simulation environment, we chose a in the simulation basis manager, the properties environment, we chose a conversion model. So we are expected to use a conversion reactor here in the simulation environment, right? So because that corresponds with the model we chose, right? So we chose a conversion reaction model, so automatically we have to use a conversion reactor, right? So this is a conversion reactor here. So we can quickly do a model for this. Yes. Okay. So 1, I'm creating my material streams. 2, and 3. I'm just going to be creating the material streams quickly. So for reactors, right? For reactors, you can actually simulate them with or without energy streams, right? So you can simulate them with or without, depending on what you are trying to achieve. So with or without. So once you are done specifying your material streams, you can add a reaction set. In this case, our set is set 1, right? So you have design, then you have reactions, right? So in reactions, you click on the drop down for reaction set and you select the reaction present. So when you click set 1, all your reactions that are in set 1 are added to that particular reactor, right? So now we can specify the let's specify the feed composition and properties. So for feed composition, for feed composition we have 0.1. For methane we have 0.1, right? Okay, so then ammonia is 0, so we just specify the composition. Then nitrogen is 0.05. So these are the mole fractions of all the reactants in the 3 reactions, right? So these are their mole fractions. Now we can click OK here. We are good with that. Then we can specify the conditions. So for conditions, I would use 500 degrees Celsius, then about 25 bar, which is 2500 kPa. Then mass flow, I just want to use 1000 kg per hour, right? So I've specified the mass flow of the feed stream, and mind you, I already specified the reaction, so automatically the whole reactor has already solved because I already attached the reaction set to the reactor, right? So we can check our composition. So this is basically what we have. So this is the feed to the process. Okay, let me see. I'll change the name. So let me change it for a clearer understanding. Let me just change their names. Okay, so we have this, and then we have this. Enter. So now looking at it with this view, we have all of this. We have the feed properties, then the product properties. So so composition, you have this for the feed. Now you see that ammonia is produced, right? Ammonia is a product of the 3rd process, and then its composition is 0, right? 0, and then you have it being produced, and some of it is in the liquid stream, and then a part of it is also in the vapor outlet, right? Now the same thing with some other reaction products as well, right? So you also have CO2 not in the feed stream, and then it's being produced, right? So this is how basically this is how it works. So let's go back to the reaction. So you have CO combining with H2O to give you CO2 and H2. So H2 is also produced from the process as well, right? H2 is also produced, and a part of the H2 that is produced is used in the production of ammonia, right? So I believe that the CH4 is used up in the process, so you don't have any CH4 coming out from this particular process. Then you have your other unreacted reactants coming out from the product outlet as well, right? So now moving on, we have okay, so like I said, you can specify an energy reaction, an energy stream if you want to, right? For example, a case where you can specify an energy stream is, let's check the temperature. So the feed to the process is 500, right? 500 degrees Celsius, right? But you see that the outlet temperature, right? Yeah, the feed temperature is 500 degrees Celsius, but the outlet temperature is 160 degrees Celsius, right? So a case where you want to maintain this 500 degrees Celsius, in a case where you want to maintain this temperature, that is, you have this as your outlet temperature as well, you have to add an energy stream, right? So the energy stream will help to actually maintain the temperature of the reactor, right? So probably some of the heat has been lost in the process, and then you have this temperature decrease, right? So during the process there is heat loss during the reactions, and then you have your temperature reducing from 500 to 160, right? So for example, if you want to maintain this temperature, you can add energy stream. If you want to get a temperature higher than this, you can also add an energy stream. If you also want to get a temperature lower as well, right, maybe even lower than 160, you can add an energy stream and specify the temperature you want in your outlet. So what I'm trying to say is, for example, if I add an energy stream, once you add an energy stream here, you can see it in your flow sheet, and then it says unknown duty, right? So you can either specify duty or you specify the outlet temperature, right? So for example, I can specify outlet temperature as 500, right, for either liquid or vapor. So for example, I specify outlet as 500. This is just an assumption for illustration, right? So once I specify that, you see the whole system solves again, right? And then the heat duty is calculated, right? Heat duty is calculated for that particular energy stream, right? 268.8 kilowatt, right? So you require 268.8 kilowatts to actually maintain that feed temperature, right? 500 degrees Celsius. So you require this amount of energy to maintain that temperature so that you can also have it in your outlet, right? So, but for example, if you maybe if you reduce it to, like, let's say 100 degrees Celsius, for example, let's say 100 degrees Celsius, right? So you still see that the system will still solve, and then the heat flow changes, right? It changes to, let's see, to minus 212.7 kilowatts, right? So you require that to actually get an outlet temperature of 100 degrees Celsius. So basically, this is how the conversion reactor works, right? So this is how it works. So the next phase of this particular tutorial is to try out the equilibrium reaction model, right? So we'll be using these same reactions to see how the equilibrium reaction model works, right? So we just want to check that out. For the equilibrium, right, for the equilibrium model, we'll use another case, but the same components. So the same components, let me remove oxygen. Oxygen is not involved in this process. So the same components and the same fluid package and the same reactions as well, right? So yeah, so we can specify our reactions again in a set. So yeah, So just click on add and then click on add reaction, right? Now in this case we are working with the equilibrium model, so equilibrium is selected and we can click on add, I believe. Yes, so we can click on add. Now we can specify all the reactions we have. Okay, let me just add, let's add 2 more, right, for the other reactions. So we are specifying the same reactions. We will be specifying the reactions again. So starting from the first, okay, so in this case for equilibrium you don't need to specify any other thing apart from stoichiometry, right? Just stoichiometry is all right for equilibrium. Then you can specify the basis as well. So for basis, okay, I'll just use molar, let's say let's use mole fraction. Let's just use mole fraction. So we are doing that for all of them. So this is the second reaction, right? Methane plus water to CO plus hydrogen. Then we have the third. The third is ammonia production. That is nitrogen. Yes, to give you ammonia. Yeah, so we have minus 0.5 minus 1.5 and 1, right? So I think we are good to go. Mole fraction, yes, let me see, mole fraction and mole fraction. So we can add to FP afterward. Just add to FP and you are good. So we can enter the simulation environment. Now for equilibrium, you can either use the Gibbs reactor or the equilibrium reactor, right? For equilibrium, specified equations or equations that were specified using the equilibrium model, you can either use the Gibbs reactor or the equilibrium reactor. So we will just be doing that quickly before this particular tutorial ends. So we go to the reactor section on the palette and we get out Gibbs reactor and the equilibrium. So just to see how they actually work, so I will just quickly create material streams. Okay, so just create material streams. Same with this, right? Let me just quickly do that. 5, sorry. Right, so just to create material streams, then we can specify the composition, right? We can specify the composition. So for the Gibbs, temperature is still 500, then pressure is still 25 bar, then mass flow is 1000, right? 1000. Then we can specify composition. Composition, you have ammonia is 0, this is 0.1, hydrogen is 0.2, hydrogen is 0.2, CO is 0.15, nitrogen is 0.05, CO2 is 0, and H2O is 0.5. Basically, this is what it is. So once you specify all of them, your stream is fully specified, and you see that okay, the Gibbs reactor has also solved. Now this is because the Gibbs reactor can actually solve without reactions, right? And let me show you how it works. So you have Gibbs reactions only, right? So for the Gibbs reactions only, the software does the calculations, right? The reaction calculations by itself without you specifying any reaction, right? So you can actually use your Gibbs reactor without reactions. So for example, if you have a chemical process and you don't know the reactions, the Gibbs reactor can be an option for you, right? So all you need to do is to specify the components, both reactants and products, in your stream, and you feed it into a Gibbs reactor, and the Gibbs reactor will do all the job for you, right? So that's it. So let's see the composition. Okay, so you can see the production of the substances. You see ammonia, you see CO2, CO, and the rest, right? So this is basically how it works. So once you specify both the reactants and products in your component list, then you enter your fraction for the stream, then the reactor can do all the calculations, right? Now another way to use the Gibbs reactor is to actually specify your reactions, right? So if you have reactions and you want to specify them, you click on this second option, which is specify equilibrium reactions, right? So once you click on it, you see this message pops up, requires a reaction set, right? So this gives you the opportunity to actually add a reaction set to your reactor, right? So by the time you just click on this, it solves, and then you are good once again, right? So we can go back to this, yes, and you see the calculations are back, right? The values of both the top and the bottom are back. So that's basically how it works. Yeah, that's basically how it works. So once you do your calculations, you get your results, right? So that's it. Let's see. Okay, so yeah, then you have the third option, which says no reactions, right? So in no reactions, your reactor turns into a separator. In that case, no products will be formed, right? So if you click on no reactions, you would see, you see it, what is coming out is exactly what is going in, right? So exactly the same composition, right? Exactly the same composition. That's what goes out. The same composition that went in is what goes out. So what it means is that no products will be formed in this case, right? Your reactor is acting as a separator. It probably a two-phase separator, right? So whatever is coming in is what is going out in this case. So you have three cases for Gibbs. You have the case where the software does the calculation for you as per reactions. Then you have where you can actually specify the equilibrium reactions, and then you have the no reaction case, right? So you can use any of them as you wish. So that's basically it for Gibbs. Then lastly for equilibrium, before we end this tutorial, is just basically the same operation as Gibbs when you have reactions in it, right? So equilibrium is like having Gibbs with reactions. So basically we'll just be doing that quickly. So we have, you just specify your properties and then your composition, and you are good to go. So that's it. I want to copy this composition. Yes, I want to copy this. Copy and just paste it in here, right? So I just want to do that. So I can paste. Okay, so I will just copy again or just paste again, right? Nah, that's wrong. Okay, so let me see if I can still copy. Okay, I know what to do. 0. Let me see if I can copy this, or let me copy it first. Copy, then let me enter just one value here and then paste the rest. Yeah, so I've copied it. Yes, so okay, yeah, so it has solved. The feed stream has solved. So for equilibrium, we still require a reaction set. So all we need to do is go to the reaction tab and we specify the reaction set, right? So once you specify it, your calculations are done and your products will also be produced, right? So basically that's how it works. So you just need to specify the reaction set for that particular reactor and it solves, right? You can also you can also specify your energy stream if you want. For example, let's see. So we are specifying the temperature outlet. So once you specify the temperature outlet, the whole model should solve once again, right? So basically this is how these models work. The conversion model, the equilibrium model, this is how they work. And with that, we have come to the end of this tutorial, this particular tutorial. So if you have questions on conversion models, equilibrium models, or whatever has been taught in this particular tutorial, kindly send in your questions in the comment section. Like this video, share with your friends, then subscribe to this channel for more notifications on videos that will be posted subsequently. Thank you for joining me in this particular tutorial. Do have a nice day.